Section 4.2, we talk about the mean value theorem. Okay, in this section there are two theorems. Okay, the first one is called the Euler theorem. Okay, Euler theorem actually is a special case of the mean value theorem. Okay, so this is theorem we're going to talk about today. And also the second theorem is called the mean value theorem. Okay, mean value theorem is more general. Okay, Euler theorem is a special case. Okay, so we'll talk about both of the two theorems. Okay, so first let's look at the Euler theorem. Okay, I'm going to ask a volunteer to read this theorem for us. Who want to read? Tyler?
Let f be a function that satisfies the following three hypotheses. If s is continuous in the closed interval a, b, f is differentiable on the open interval a, b, f a equals f b, then there is a number c in a, b such that f prime equals 0.
Okay, f of prime and c equals 0. Okay, okay, very good. Okay, let's look at what does Euler theorem tell us. Okay, if a function satisfies these three hypotheses. Okay. Yeah, hypothesis. Okay, yeah. How do you pronounce it? Hypothesis. Okay, hypothesis. Okay. The first one is this function is continuous on the closed interval a to b. How do you understand a function is continuous? No gaps, no holes, and then if you draw the curve right on the interval, you don't have to lift your pen, right? So that kind of function is called continuous. And I believe the Jason covered this section for us, right? What is a continuous function, right? Alright, so continuous on the closed interval, okay? Or the specific definition is if a function is continuous at a number a, if what? The limit of f of x when x approaches a from both directions must equals what? F of a. So we did this in the previous section already. I'm not going to review that, but this is when a function is continuous at a point, okay? Then if a function is continuous on every point on that interval, it is closed. It is continuous on the closed interval. Okay. Yeah. So this is something that we learned before. First hypothesis. Second one, if f is differentiable on the open interval a and b, you see, they get rid of the endpoints from that interval. Okay. F is differentiable on the open interval a and b. How do you understand a function is differentiable on the interval? If f is differentiable on the interval, that means f is differentiable on every single point in that interval, right? Say, this is c, okay, number c between a and b, okay, now open interval. So how do we understand the function is differentiable at this number c?
It just kind of a corner.
What?
The function can't have a corner.
No. Okay. So that means, okay, a function is differentiable at the c means what? If we differentiate f and then we evaluate the derivative of f, it exists. Okay. So f prime of c exists, then we say f is differentiable at c. Okay. How do you understand f is differentiable on the interval? If f prime of every point in between of the interval exists, then it is called differentiable on the entire interval. Okay. But we don't talk about when the derivative at its endpoint. We don't talk about that.
Right, that's not what I meant. I was assuming that if it's continuous, like there's some functions that are continuous but not differentiable, and those are the only functions that have a corner. Otherwise, it's differentiable.
Yeah.
That's what I meant.
Yeah. But you're talking about a corner thing?
Yeah, that's the only time when it's continuous but not differentiable.
Yeah. The corner. It's in our textbook, right?
Yeah.
Yeah. But here, I want to see that when we are, evaluating, verifying the hypothesis, here most of the questions we don't have the corner, okay? But we have to pay attention to at the end point, we don't include the end point. Okay, so this is something that later there are many questions that you have to verify the hypothesis. Make sure when it is continuous, it's on the closed interval. When it is differentiable, it's on the open interval. Okay, yeah. All right. Third hypothesis is f of a equals f of b. Okay, the value of f at the two endpoints must equal each other. If all of the three hypotheses satisfies, then we say there is a number c in this open interval, okay, such that the derivative of c equals 0. What does the derivative of f at c equals 0? That means we must have what? A local maximum or local minimum values at when f is at c. That means we always will have what? Oh, the tangent line to the curve at when x equals c is what? 0. Okay. All right. So these are the cases, different cases. Okay. So if we have a horizontal line from A to B, okay, it is continuous on A to B, closed interval, differentiable on the open interval A to B, and then f of A equals f of B. So there is a c in A and B such that f prime of c equals 0. Actually, every point between A and B are what? The c's, right? Because it is a horizontal line, right? Well, this is a case when what? Oh, this is a continuous function, okay, continuous function, okay? So f of a equals f of b, continuous differentiable, c, there must be some c, okay, such that f prime of c equals 0, okay? Same thing here, there must be more, than one local maximum, local minimum. So we have one local maximum, one local minimum. Yes, we do have f prime of c equals 0, okay? This case is what? Oh, f of a and f of b are the largest values, okay, on the, when x is between a and b. But however, we still have a what? Local minimum. So this is also f prime of c equals 0, okay? So this theorem is telling us what? As long as a function f satisfies the three hypotheses, there are always exist a number c or multiple number of c such that the derivative of f at c equals what? 0. Okay. Alright, now example. We have question A and B, okay? Let's do B together. Okay, you can try A. I'll let you practice A later, in a later time. Verify that this function satisfies all of the three hypotheses of the Euler's theorem, okay? And then find a C such that it satisfies the conclusion of the Euler's theorem. Verify this function is continuous on the closed interval, right? Is it closed? Is it continuous on the closed interval? See, f of x, this pi over 2 to 3 pi over 2, that's for what? X, okay? So when x varies between pi over 2 to 3 pi over 2. Now, we have our function signal pi x over 2. So if x varies between pi halves to 3 pi halves, how about x over 2? X over 2 will varies between what? Pi fourths to what? 3 pi fourths. You guys agree with that? Okay, the thing is, well, sin of x over 2, okay, continuous on pi over 4 to 3 pi over 4. Let's draw the picture. X over 2 for the horizontal axis, okay? So sin of x over 2, okay? So we know that sin function always looks like this, and so on, okay? So this is when x over 2 is between what? Pi fourths to what? 3 pi over 2. 3 pi over 4. This is pi. Okay. So actually, x over 2, we cannot count this, right? We can only count this part. Right? So this means when x over 2 is between, when x over 2, this is a sin of x over 2, okay? When x over 2 is between pi fourths to 3 pi over 4. Do you think this function is continuous on the closed interval? What do you think? It is continuous? Yes. So we say yes. So 1, okay, f is what? Continuous on the closed interval. Okay, I will still say pi over 2 to 3 pi over 2 because that's for x, okay? Well, x over 2 is between pi fourths to 3 pi over 4, but x is still between pi half to 3 pi over 2. Alright. Now, secondly, is this function f differentiable on the open interval? This is the graph of the function. Do you see anything strange? Broken or anything? No. And the sine function is differentiable, right? What's the derivative of sine function? Cosine, right? There's no anything abnormal or like looks strange or anything. So yes, number 2, f is what? F is differentiable on the open interval, what? Pi halves to what? 3 pi over 2, right? Third hypothesis. What is third hypothesis? How about f of a equals f of b? What is f of a? F of pi halves. What is f of pi halves? When x equals pi half, x over 2 should be what? Pi fourths, right? Sin pi fourths. If it equals f of 3 pi over 2,
Well, it repeats every 2 pi, so it should be.
So if x equals 3 pi over 2, it's going to be sin of what? 3 pi over 2 divided by 2. 3 pi over 4, right? Are these two numbers have the same value? Check your unit circle, okay? Yes, they are. This equals square root of 2 over 2. This also equals square root 2 over 2. So yes, they are equals. Alright, so because all of the 3 hypotheses was satisfied, then by Euler's theorem, okay, so then, okay, there must exist a C, okay, there exists a C, okay, in what? Between pi over 2 to 3 pi over 2, such that what? The derivative of f, okay, the derivative of f. What is the derivative of f? Let's compute it here. What is the derivative of f? Cosine of pi over 2 times by chain rule, x over 2's derivative with respect to x, 1/2, right? So there must exist a C such that f prime of C equals what? 0. So 1/2 cosine of what? C over 2 must be what? 0. Then we can find this C. You guys, everybody? See, the conclusion is there must be a C in A and B such that the derivative of f at C equals 0. So our function's derivative is 1/2 cosine of x over 2. F prime of C must equal 0. So we're going to find this C, right? So how? Cosine C over 2 equals 0 implies cosine of C over 2 equals what? 0. Why? Because both sides multiplied by 2 give us what? Yeah. Right side is 0, left hand side is cosine of C over 2. Cosine function equals 0. Do you still remember the cosine function, what it looks like? Oh, this is too tall. This is x, this is cosine of x, okay, y equals cosine of x. And where does cosine function equal 0? Pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on, right? So when cosine of c over 2 equals 0, the c over 2 must equal what? Either this, or this, or this, or this, or this, right? So I'm going to choose some of them, okay? Blah, blah, blah. Negative pi over 2, pi over 2, 3 pi over 2, and so on, right? Well, if c over 2 equals this, c must equal what? Blah, blah. Negative pi, pi, 3 pi, 5 pi, because this is 5 pi over 2, and so on, right guys? You guys? However, can we choose all of these c's? Yeah, our c can only vary between pi over half to 3 pi over 2. So, which of these values satisfy? It's between pi halves to 3 pi over 2. You are right. So the answer is this c must equals pi. Okay? C must equals pi. You guys, was good? Okay. Yeah, the reason why I'm using this question is because this question is a trig function, so I'm thinking that maybe I should do this, we should do this together, right? And then the other question, you can try this later in practice, okay? Yeah, I'll let you try this one, okay, in group, okay? Alright, so this is a Euler's theorem, okay, Euler's theorem. Let's see, do you want to practice first or continue doing the mean value theorem? Okay,